what, first of all, yesterday my internet fell in the beginning of the class and it took hours to come back. But it's okay since it came back, so I hope it will not happen today. But if I disappear, maybe it's what happened. Sorry, just a moment. A few things. So, course evaluation, please fill it. Sorry. Because not only for everybody, for the university in general, this semester is very important because all of the things that everybody is learning regarding remote teaching, and there are things that there are advantages and disadvantages, obviously, like everything in life. And so it's really a lot of questions and a lot of decisions. So please complete the course evaluation. And for me also specifically, it's very, very important. So if you haven't done, please do. Now, I have a question for you guys. Some people have been asking me whether I'm going to teach next semester and what I'm going to... So one possibility that may happen, I don't know, it will depend how many students are interested. And even if there are many, it's not sure it will be possible. But maybe I'll offer a seminar in the fall about all the... First of all, in the fall we'll have in-person classes, so it will be fun again. Not that I haven't enjoyed. Anyways, so a seminar, small, based on discussion, and the content that I'm thinking about is all the big questions about science, about epistemology, not philosophy, but a little bit of philosophy, about decision making and emotions, and how do we know that we know what we think we know, and all these big questions. So that's so I'd like to ask you. Let me open here a poll. It's anonymous. So the question is whether you would be interested. Can you see it? Whether you would be interested in enrolling it. All right. Thank you. Good. Very good. I'll leave it open. Maybe other people will join us later. Let me just... So we are going to talk today about localization, which is... we have a lot to talk about it. And... and it's probably... It's hard to cover everything in one lecture. I'll try as much as I can. Let's see what happens by the end of this class. If maybe I'll continue into the office hours, and whoever has to go, you can later see the rest in the recording, or or on next Monday in our last lecture. Probably I still want to cover motion a little bit. Perception and action, that is in the syllabus, is the how do you call it in English? Every semester, perception and action, every time it falls out. Also, it sounds interesting. I don't know if it's. I think. Let's see. I think motion is more interesting. Okay, so today we are going. Why it's not working? So, sound localization is our perception of the direction from where sounds come, and we are pretty good in assessing and estimating the direction from sound. Not perfectly good, but we are good in it. And actually, it's a big thing. Sound localization is much more important and present and critical in our daily life than we are aware of. It's not something we think about. If 2-3 lectures ago I asked you about how important, what's more important, sound, hearing or vision, and it's not clear, but hearing. So the same localization is a big thing in hearing, and we mammals, we have a lot of independent alternative mechanisms that work at the same time upon which we interpret directions from sound, which suggests maybe in hindsight, if we want to look like that in evolution probably it played a very crucial role for survival and mating or only for mating, I don't know. Okay, so let's begin with the brain. And I know you guys love to talk about the brain because you think it's cool. So there are two basic neuroanatomical principles that I would like to tell you about that are important for sound localization. So what we have here is a coronal slice of the brain. So the face is looking at us, and we have the right ear and the left ear. And so far we have talked about how air pressure waves are transducted into neuronal action potentials. And it happens here, right? That's what we saw until now. So let me just remind you what we saw. So auditory canal, the drum, the middle ear, and then this is the cochlea unrolled, and our basilar membrane that separates spatially the frequencies, right? So here we have the auditory canal, the eardrum, the three ossicles, and then here the stape, the foot plate, transmits air vibrations into the cochlea where there is liquid, and the basilar membrane is rolled up here. We always look at the basilar membrane stretched, but it's in fact rolled up inside here. And we stopped here. And then from the hair cells, if you remember, we have the auditory nerve fibers that here we cannot see. It's behind the cochlea, that they leave and go to the brain. And it's these guys here. And the first important place they bound together is the cochlear nucleus. We have two cochlear nuclei, so one nucleus on each side. And nucleus here, it means like in neuroanatomy, when we can say nucleus for one cell, the nucleus of a neuron, of a cell, but nucleus also is a hub, a cluster of a high concentration of thousands and thousands of cells that receive axons from a given area, that we assume to pertain to a given function, and they send or divide into other stages along a given pathway. So the cochlear nucleus, as the name implies, receives all the axons, all the information from the cochlea. And these two little arrows here are very important for the auditory system, okay? Which is the first place where information from both ears is integrated. So the right cochlear nucleus receives all the information from the cochlea and sends, we cannot see the bundles, only the arrows, sends this information, or part of this information, to the left superior olivary nucleus, which is the second hub after the cochlear nucleus. So these two are the olivary nuclei, so both of these, they receive information from their side and also information from the other side. And this integration of information from both sides is crucial for the auditory system more than any other sense. So it's not that it's not a crossing of information. It's not the all information from the left side is sent to the other side. It's only that the other side is updated about what's going on the other side. It's integration, it's not swap of information. Most of the information of the left ear is processed in the right hemisphere, in the auditory cortex, in the temporal lobe. But after the olivary nuclei, both sides have integrated information from sounds that arrived in both ears. Okay, so this is the first principle, neuroanatomic principle, that we want to know. And the second is that all the cells along the entire auditory pathway are organized tonotopically. I'll explain. Like, this is the auditory pathway from the ear through the nuclei. There are other important hubs on the way. Each hub does something slightly or sometimes very different until the auditory cortex, but they are all tonotopically organized. So as you already know, all the thousands of different frequencies with different amplitudes that comprise any given complex sound that reaches our ear at any given moment, they all arrive at the same time, combined together in one stimulus. So they arrive to the outer ear, they enter, the middle ear modulates everything, but transmits the entire complex sound in one bunch, in one stimulus per time to the inner ear. And only inside the cochlea, along the basilar membrane, that a complex sound is separated into its many components, into different frequencies, and they are separated spatially. They are distributed along the length of the basilar membrane in a numerical order. As you remember, closer to the base we have the higher frequencies, and then the frequencies, the numerical order of the frequencies decrease until the lowest frequencies that we can hear along the apex of the basilar membrane. So from the basilar membrane, from that point on, from the cochlea, this same spatial organization according to frequencies, which is the tonotopic organization, tonus, tone, topic on the surface, organization is preserved along all the processing hubs and stages up to the auditory cortex on both temporal lobes. So this is the temporal lobe. This is the primary and secondary auditory cortex. The same. So this tonotopic organization or map is also called the cochleotopic map because it was determined inside the cochlea. Actually, it should be called frequency topic organization because it's anchored on the sound frequencies. Tone is our perception. Tone is more, it's pitch, is our perception of the frequency. But never mind, this is pure semantics. And this organization is parallel to something that we already saw in the visual system that is similarly organized in its entirety, along its entire pathway from the retina until the visual cortex in the occipital lobe. They all remained spatially arranged according to the spatial organization of the photoreceptors on our retina, right? Okay, so what we see here is a slice from a cochlear nucleus from an animal. So this names here is anterior, CN is cochlear nucleus. So this is anterior ventral, this is dorsal, posterior ventral, never mind. These are different regions inside the cochlear nucleus of an animal. Now, I am going to describe verbally, no pictures, of how it's done. So if you don't want to hear, mute. Some people are very sensitive to that. That's what I am saying. So when I move back to the next slide, you can come back to listen. So the animal is alive under anesthesia, and then many hundreds of electrodes for single cell recordings. They are implanted one at a time or sometimes some together in different areas within the cochlear nucleus in this case or other places. This is the same idea for all the other. And then many different sounds are presented to the animal, different frequencies, and the action potentials, the activity, the neural activity of each one of those cells attached to one electrode is recorded one by one. Now this is it's a very complex and finicky procedure, because I told you when we talked about the grandmother cell, you have to insert a lot of electrodes until it's by trial and error, until you have an electrode with a clear recording, which means that it's probably touching only one cell, an axon, and the connectivity is good enough so you can hear the spikes clearly. And then for each one of those electrodes, you have to present all the range of sound frequencies that you want to assess until you find one specific narrow range of frequency that each one of those cells react most, like it's sensitive to it. And then you have to repeat this entire process, this entire procedure across one by one of those recording cells, and across many different areas. So one experiment like this with one animal can last for days, many days. In the end, the animal is euthanized, it's sacrificed, and then the tissue from which it was recorded is dissected, and only then it can be seen exactly where the electrodes were touching their point, from where exactly they were recording. And then we can finally map what is going on in that area. So what you see here is a slice of the cochlear nucleus from an animal, for which the activity was recorded. And what we can see is the arrangement according to frequency of specific cells and their sensitivity, their respective preferred frequencies. So here we can see that along this area the cells are organized from 3,500 hertz, increasing up to 18,000 hertz. And then in this adjacent area, this organization repeats itself. Here, or partially repeats itself from 9,000 hertz to 15,000 hertz. And this same serial organization repeats itself in many different areas, in the same tissue, in the same nucleus, here in this case the cochlear nucleus. So the cochlear nucleus is here, and the next slide we are going to see the same tonotopic organization inside the inferior colliculus, these two guys here, which they are the third hub along the pathway. This looks like a cat brain. I don't know if it is. Maybe it's a rat. We can see here, so this is the cross. We can see that these cells, they are sensitive to 2000 hertz, and these to 21,000 hertz. And they are organized serially here in an increasing order. So there is, along the entire pathway, there is a correlation between geographical position, space, and numerical frequency. And it continues up to the auditory cortex, as I just said. We can see that it's the same thing. All right. So now we are going to leave the brain and we are going to talk about physics. Back to sound propagation. So first of all, let's go through some terminology. We want to describe, in order to ground psychophysical or physical experiments, first of all we have to describe directions in a three-dimensional space. So we need three coordinates. We could use three Cartesian axes like x, y, and z. We could use many other denotations, but by convention, for sound localization, we use azimuth, elevation, and distance, which is similar to how we describe the Earth, positions along the Earth, the surface of the Earth. So imagine a sphere, a globe, and the head of the listener is the center of the sphere, of the globe. So azimuth refers to the horizontal, a two-dimensional horizontal plane parallel to the surface of the Earth, right? So we are looking from the top, as we can see from this dumb drawing here. So azimuth is the horizontal direction along a imaginary circle of 360 degrees, and the head is in the center. And that would be the longitude, if we are talking about Earth. So by convention, in front of the face, we have 0 degrees, and to the right, we have positive azimuth numbers in degrees. To the left, until 180. So to the left, we can either say negative numbers. So here we could say minus 90 or 270 degrees, right? Coming from this side. And straight from the back, we would have 180 degrees. And any number in between. Clear, right? Elevation would be a circle vertically around the head of the listener. Okay, you can see it. And that would be like latitude in terms of Earth. So above eye level, from above, any direction from above is a positive elevation, and from below it's a negative elevation. So here we have all the 3 coordinates together. Azimuth would be, from her point of view, left or right. And elevation, up and down. And the third coordinate, distance, is distance. I don't have to explain. Okay, so let's begin with azimuth, okay? We are going to talk only about azimuth now. Only about horizontal information, physical information that is part of sound propagation. We have 2 physical phenomena that our perception system heavily relies in order to estimate direction from which a given sound comes from. So we are talking only about the horizontal plane. So the first one is interaural level difference, ILD. And the second one is interaural timing difference, ITD. Interaural is interaural, the 2 ears, okay? Orecchia in Italian. So these are physical phenomena, again, and they occur at the same time for every given sound. They are more or less this difference, so the difference between the 2 ears in terms of intensity and timing can be more or less significant, more or less useful for our perceptual system to identify directions. And depending on the circumstance, we'll see exactly how. So let's assume a sound source coming from this direction, and we can see 2 important differences between how this sound, these air pressure waves, reach each one of the 2 ears. So first of all, the sound reaches this ear, one ear, before it reaches the farther ear. So we have a difference in time. And sound speed at sea level is around 340 meters per second. And it may seem to you that this is a miser, almost insignificant difference, but it is. And later we'll calculate it. The second is that the sound quality, the sound itself, is different for the further away ear, because the head obstructs those airwaves. It dampens, or partially dampens, the sound, so it causes what is called an acoustic shadow behind the ear. And this is, when it happens, we have interaural level difference, and the difference in time is interaural time difference, when there is. Okay? So let's begin with interaural level difference, intensity difference. First of all, we can see that the interaction of the head with the sound depends on the sound frequency or frequencies. So the head obstructs or distorts or changes high frequencies much more than low frequencies, because as we can see here in the picture, the difference between the phases is relative, is small relative to the size of the head. But for a low frequency, depending on how low, the head can be hardly significant, because each wave passes by the head, which is okay, you understand. So if we try to calculate a 6,000 hertz frequency, so 340 milliseconds, 6,000 hertz is 6,000 cycles in 1 second, right? So if we multiply, calculate, it will be 0.05 meters, it's 5 centimeters, which is something like this, no, 5 centimeters, with 3 inches, something like that, 2 inches. Yes, 1 inch is 2.45 centimeters, so it's exactly 2 inches, which is, and our head is something like 7 inches, something like this, right? My head is not, 7 inches. So for 6,000 hertz, the head is big enough to distort it. But for 200 hertz, if we calculate the distance between each how do you call it? The wave, an entire wave is 1.7 meters. That would be almost less than almost 6 feet. So the head is very small. By the way, this is wrong here. Imagine that 6 feet, if this is the head, 6 feet would be a tall person. It would be something this big. So this drawing is wrong. This drawing would be something like, if this is 6, would be something like 800 hertz or 900 hertz. But which is still low enough to jump over for the head to hardly affect this frequency. All right? Now, even for low frequencies, there will be a difference between the two ears if the sound comes from certain directions. If it comes from the front, there will be, the sound will reach both, or from the back, the sound will reach the two ears identically, even if there is some minor distortion by, I don't know, this part of the head, but there won't be a difference between the two ears, right? Okay, so here we can see, so by the way, ILD and IID, ILD is interaural level difference, IID is interaural intensity difference, is exactly the same. So here we have the difference between the two ears in decibels. Here we have the direction in azimuth from where the sound comes. And we can see, and here we have different frequencies. So we can see that if the sound, and here we can see the azimuths themselves. If the sound comes from zero degrees, or from 180 degrees from the front or from the back, the difference is zero for both, independent of the frequency of the sound, because again, it reaches both sounds identically. Now, the more it comes from one of the sides, reaching the maximum difference at 90 degrees or 270 degrees, this would be the maximum difference in level, we can see the interaction between the direction and the frequency. For a low frequency sound of 250 hertz, there will hardly be any difference between the two ears. The head will hardly affect it. It will be like 2 decibels. But for a 10,000 hertz sound, the head will dampen, will decrease the intensity by 20 decibels. That's a lot, right? If you remember, 20 decibels, it's a difference in amplitude, 10 times difference in decibels. So one ear, 10,000 hertz, one ear will hear the same sound 10 times lower. So for your reference, an earplug, normal earplugs, they decrease the amplitude of sounds by 30 decibels maximum, or at least their exaggerated marketing on the box, sometimes it's written 40 decibels. Doubt if it reaches, but so 20 decibels, it's a lot. Okay, so the previous graph that looked so nice and perfect, these are for theoretical estimations. And this one is based on actual measurements of a real human head with real sounds. What you have here is frequency on the abscissa, right? And the difference in intensity, in decibels, between the two ears. First of all, we can see, as we already said, that the head begins to affect the sound beyond here, 500 hertz, and then it grows up. So what you have here, these 3 lines, are sounds coming from 10 degrees, 45 degrees, and 90 degrees azimuth. Who wants to tell me which one is the 90 degrees, the 45 degrees, and the 10 degrees? Write down in the chat. So we have 10, 45, and 90. 90, 10 is close to in front, 90 degrees is from the side, right? We can see, no one wants to try. We can see that one of them makes a big difference for high frequencies. Okay, so this would be the 90 degrees, because 90 degrees is the position, the direction from which a sound comes that the head will affect the most. So that would be is it green? Blue? Well, you guys see the colors, right? So this is 90 degrees coming from the side. This is 45 degrees because it's medium. And the least difference, the least dampening effect would be 10 degrees. Question, let me give you a poll. Can you see the poll? Minus 90 degrees and 90 degrees is exactly the same, right? It's from 90 degrees is by convention from the right side, minus 90 from the left side. All right. Okay. Yes. Well, it's not an easy question. It's not an easy question. So let's look at it. Almost everybody did. So 2000 hertz would be more or less like here. 40 decibels would be more or less like here. And this is 45, which is identical to minus 45. So the answer is B. Make sense to everybody? Not clear to anyone? Okay. Next, what time is it? When did we begin? We have half an hour? 3:30, 4:30? We have half an hour. Okay. Let's talk about the differences in time. Let's see. So let's assume, so this is a low frequency sound, which is not affected by the head. So we can talk about only the difference in time. Let's say it's coming from this direction. So this little red segment, green or red segment, is the additional distance that this sound has to travel until it reaches the left ear after it reached the right ear. Okay, so we can calculate this little difference compared to when the sound comes from straight ahead. So it's not too complicated. I don't know why it's oval supposed to be a perfect circle. So let's try. Let's calculate. So for the simplicity of the calculation, let's, for this example, assume that sound is traveling at 300 meters per second instead of 340. So the size of the head is more or less 30 centimeters. That's a big head. That's actually a huge head. So how long will it take anyone? Zero 3, so that would be like 3000 divided by 3, 1 by, that would be 1 second divided by 1000. That would mean, for this number, that it takes 1 millisecond, that's nothing, longer for this sound to arrive to this ear in the worst case scenario or in the best case scenario. The maximum difference in timing is when a sound comes perfectly from one of the sides at head level, because if it's elevated, the distance, right? If it comes from above, this from the side, but above or below, geometrically, this distance will be smaller, right? You can visualize it. 1 millisecond. So, but this was with 300 meters per second. Let's see the real numbers, or more more accurate numbers. So what we have here is in microseconds, all right? Which would be 0.00 milliseconds. So from the largest time difference between the two ears, which is when it comes from head height, eye level, from one of the two sides, is 640 microseconds, which is 2/3 of a millisecond. And you would say, that's all. But yeah, that's it, and it makes a difference. Okay, now, let me see for a moment. Start thinking. Yes, perfect, Caitlin. We can see here that for any given moment, this sound wave arrives first. So from here it would be exactly the same time, but from the side, this one arrives first. Now, this is a 200 Hertz sound, a very low frequency sound. Let's see what happens for a high frequency, or a higher, it's only 1000 Hertz. Can you say, looking at the graph, which one arrives first? No. The answer is C, we cannot say. Why? Not only because of the drawing, but because we said that the distance, the time that it takes from one ear to the other, in the largest difference in time would be 2/3 of a millisecond, 640 microseconds. For a high frequency sound, 1 millisecond or less than 1 millisecond, there are too many cycles going. So our system cannot differentiate. There is much less information. Let's say that for a high frequency sound, 1 millisecond afterwards, the difference would be, let's say, I don't know, 700 cycles compared to 640 cycles. A low frequency sound would be 2 cycles compared to 1 cycle, because in 1 millisecond there is much less cycles. So in terms of vibration, our system there is not enough information for our system to use this time difference when you have a high frequency sound. It's mainly for low frequency sounds, all right? Interaural time differences is a useful cue to localize sound. Well, I just said for low frequencies and for azimuth, right? when the sound comes from eye level, from the same height as the head, because if it comes from above, the higher the elevation or the lower the elevation, the less the difference in timing between the two ears. You can see it, right? So the answer is C. This you already know, it's an easy one. Okay, let me tell for a moment. So if we were in class, I always do it. It works, it's unbelievable. Try it at home now. Try to make like a bet. That's how bets actually Bats, by the way, they also use sight, but for longer distance. They sometimes cross cities, they cross miles and miles until they reach wherever they want to reach at night. So then they use vision. But for when they are hunting, when they are in close quarters or close to things, they use sound, as you know. And it's high-pitched. Because high-pitched sound, you have more, it's... now, try to do like... So we can also do that. More than you think. Try to do... close your sound so the others can... Try to do a high-pitched sound like this. If... And this is a demonstration I used to do in class. You close your eyes, do this sound. You have to do it all the time, like emit it one after the other. Close your... And then, sorry, look to me again. And then put a book or something in front of your face, like this, and move it. Okay? So do like, close your eyes and... You will clearly see the difference. You can really follow the object. So in class, close your eyes and I put, and always the volunteer always can say where I am putting the book. In the army, you probably saw it in movies. In the army, when you are in a mission at night, and this is one of the few things that are real between movies and reality. When you are at night, when you are moving, you want to remain inconspicuous, you want to call the attention of another soldier, they do. Like this sound. Now, it works. So the legend, at least when I was in the army, they explained to us because it sounds like, little animals, nocturnal animals or insects, whatever. But I never heard animals that do this, at least in the places I've been, other animals that do. So, but we can offer a more plausible and educated explanation for that. So first of all, this sound because it's high-pitched, and if we move our ears, that we'll see soon, we can easily localize it, okay, because of the interaural level difference, not timing. Timing, we just said it's only for low frequencies. But for close by, or at least in the distance that soldiers are one from the other, some yards, okay, the interaural level difference between the two ears work really well. So whenever you hear, you can really fast localize where it's coming from. And the second thing is that low frequencies, as we just saw, they interact much more with objects and everything around. And they don't travel far. Low frequencies, they travel far. That's why elephants, or big animals that they have to call each other from far away, they emit low frequency sounds. So soldiers trying to remain covered, so this very high pitched, it's one of the higher pitch sounds that we humans can do, doesn't travel too far. That's it. Next. Okay, so here we can see the difference in timing. We are back to timing, okay? The difference in timing for different directions. So this is difference in time, and this is the azimuth. So when it comes from straight ahead, 90 degrees or 180 degrees, there is no difference in time between the two ears. When it's when it's 0 or 180, there is no difference, 0. When it's 90 degrees or 270 degrees, it's the highest difference in timing between the two ears. Now, look, if the sound is coming from, let's say, 60 degrees, the difference is 0.45 milliseconds, which is the same if the sound is coming from 120. So, if the sound is coming from here, okay, or from here, it's the same difference in time. And if it's a low frequency sound, for which we don't have inter-hour level difference, and we have only interaural time difference, we cannot differentiate this direction from this direction. Make sense? Because it's the same difference in time. And if we and also if it come from different elevations, so the higher the elevation, the less the difference in time, because the less the difference in distance. So in certain circumstances, our ability to accurately localize directions becomes limited. And this is called the cone of confusion, as this woman clearly expresses. She is confused whether the sound comes from A or from B. And one way that we partially resolve it is by turning or moving our head, which allows for the system to collect different interaural differences in sequence from the same sound, and then compare them together and better estimate the direction. And the second thing that we use is by analyzing the way different frequencies interact with our pinna and our head. Finally, why our pinna? Why this flap or thing looks the way it looks? It's not nothing. I almost told a very good joke. Almost. So let's see how it works. So it works mainly for elevation. So these are, until now we talked about the difference between the two ears. Monoaural cues are those that the entire information is present in each ear by itself. And as I just said, it's very useful for elevation, although if we move our head, it's useful for many things. And it's a consequence of the asymmetrical anatomy of a pinna. Asymmetrical, not between the two ears, but an ear in itself. It is as ugly as an ostrich. So different combinations of directions and frequency, they resonate and they bounce differently on the surface of the pinna. And then different combinations of that sound end up entering the auditory canal. Let's see exactly how it works. I have 10 minutes, all right. So this is an illustration of how different sounds from different elevations, they bounce and they enter the auditory canal. And this is called the HRTF, the head-related transfer function. It should be the pinna-related transfer function. It's mostly the pinna, but for each head has its own pinna, so that's two pinnas, pinnae, is how different frequencies interact with a given specific pinna depending on their elevation. Each frequency, each elevation, each pinna. So each person has, assuming that the two pinnae are identical, which they are similar, never identical, but the HRTF is similar for the two pinnas usually, but it's completely different for different people. So each HRTF, each head-related transfer function, is unique for each pinna, so it's unique for each person. And the word filtering here, the specter of the frequencies, filtering meaning implies that some frequencies are filtered out. They are blocked, they do not enter, they are, or at least attenuated, and they do not enter the auditory canal. Okay, so what we have here, this is elevation. So here is a sound coming from head height. This is a sound coming from above, almost from the top, right? 90 degrees would be exactly from the top. And minus 60 is from below, from far below. And what we have here is the attenuation that a pinna does to each frequency. Here we have frequencies, how the pinna attenuates the different frequencies and allows some frequencies to enter the auditory canal and others not. All right, so let's look more clearly. So the difference between these two lines, the solid and the dashed line, are two different people, two different pinnae. So we can see here that for the solid line, first of all, we can see that the attenuation starts, it's mostly for high frequencies. So attenuation, the minus, means that it blocks. Positive numbers should imply an amplification. Maybe there is a little bit. I don't know if it makes sense to me, but there are many things that don't make sense to me, and even though they exist. So what we can see here is that for this person, the solid line, frequencies around 6,000 hertz, they are critically blocked, filter out, but 8,000 hertz not. And this different person, this other pinna, completely different story. All right? Now, if each person has its own pinna, sounds funny, and each pinna has its own unique head-related transfer function, it means that a person's interpretation, a person's perception of elevation is fully dependent on this person being able to interpret the function from its own ear, this specific function, which means that the person learns how to do it. Okay, let's see how. This is another example of this is the same person, the same pinna, different elevations from above and below. We can see how unique, how differently the pinna modulates the sound, the frequencies. So as soon as, and we do it very fast, and we continue to do it because our ears continue to change along our entire lives, not only until adulthood, but also any cartilage. No, that's why Jews, no. That's why old people have bigger noses and bigger ears. because cartilage continue to grow. And so we are all the time learning this function, and we use it. And so when we move our head or tilt any movement like this, we change the entire spectrum entering the auditory canal. And from that, because we know the function by heart, we can estimate elevation pretty well. Okay, so this is an experiment in which the same participant estimated the sound direction across 5 different conditions at 5 different times. So what they did, they inserted a mode inside the pinna of the participant, which obviously changed the anatomy, which changed the head-related transfer function of the pinna. And the participant remained with the mode inside the pinna for 19 days consecutively, okay? So first the participant was tested just before the mode was inserted, and then immediately after inserting the mode, 5 days after, 19 days after, and then they removed the mode, and again they tested the participant. Now let's see what we have in each one of these graphs. Here we have azimuth in degrees, so this is exactly in front of the person, minus 30 degrees from the left, something like this, if you can, well, you cannot see me, but from the left, 30 from the right, and this is elevation from head, from eye level, from above, not too high above, it will be like this, and from below like this, okay? So we have 16 different directions. So the blue grid, the straight grid here in the back, they represent the coordinates of 16 different sounds. Each intersection is one position. So we have 1, 2, 3, 4 from above, 4 from a little bit above eye level, 4 from a little bit below, and from down below. That would be minus 20 degrees, 20 degrees, okay, you see it. And from 2 from the left, not too much from the left, these are small difference in direction, okay? And 2 from the right. And this other distorted grid, red or green, each point is the person's estimation, perception, perceived localization, direction of the sound, all right? We can see it's not perfect. So first of all, this is the person before the mode. This is the day-to-day estimation of this person, this specific person. So this not bad at all, with a little bit bias for the left side for some reason. And then immediately after inserting the mode, we can see that on the azimuth, meaning left or right, perception of this person remain intact, exactly the same. Look, it would be this. Compared to this, it's exactly the same. But the elevation perception completely disappeared. Because azimuth, as we saw before, can rely on interaural time differences, interaural level differences, while elevation depends on the head-related function, right? After 5 days, and then we can see that the person starts to learn how to interpret it. Very fast. Look, after 19 days, not bad at all. It's impressive how fast. I was surprised the first time I saw it. How fast a person can learn. So this is the first interesting thing that we see here. The second very interesting thing is that immediately after removing the mode, the person immediately remembered and effectively interpret the localizations with the original function. Interesting, no? I think, what time is it? Okay, I will say a few words, 2 minutes, about distance, and then we'll wrap up. So distance can be inferred from different independent pieces of information. None of them are very accurate, and they are used together. So sound level works either by comparison, if we are hearing the same sound getting closer or getting further away, we can assume that if the sound level is increasing, so the source is getting closer, or by expectations, by prior knowledge, by top-down expectations for sounds that we think, we assume that we know expected levels. Frequency, as we said before, interacts with distance because higher frequencies, they are distorted by objects on the way or by air turbulence, much more than low frequencies. That's why from far away we can hear, let's say in a party, we hear only the boom, 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 boom. For those of you that find yourselves in nature looking for the rave party, you follow the boom, 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 but you cannot hear the high frequencies. Head movement, it works for closer or medium close, mostly for closer frequency distances. By moving our head, we can change the interaural differences, and depending if it's close enough, we can interpret an approximation of probable distances by differences in amplitude between. Like if you get closer and further, if it's close, if it's not too far a sound, if you move, then you can infer probable distances. And reflection or echo can also provide hints from distances if we are in a place that sound is bounced, that there is some kind of echo, and if it's not too far away, if it's close quarters or short distances, maybe a little bit more, because then the same sound reaches us with different time lags, different time delays, and then sometimes we can infer the distance, the probable distance of the sound. We did it. Maybe I'll decide, maybe next time I'll add some more stuff about localization, but we did most of it. All right? Questions?